Hey everybody, Lars here. Time for the review video for Unit 4, Video 1. And we're going to do the first half of the slides tonight. We're going to talk about sorting, we're going to talk about searching, and we're going to talk about Big O, the analysis of algorithms. But here's the trick. As you know, spring break was crazy, and I went to Seattle, and then I had to come home. And then we got hit with the monster snowstorm. And then I had a basketball party. Every time the NCAA basketball party happens, as odd as it may seem, I played basketball when I was a kid. So my basketball team and all of my friends, about 25, 30 people come over, and we watch all of the games for 4 straight days. We have a big party. It's called the NCAA party. And I was throwing my party for the last 4 days. So I literally have been awful. I haven't done a blessed thing. So I need to catch up in the worst way. And I know you guys are part of that. I got to get you 2 videos. I got to get you the homework assignments. I've got to get you up to speed as far as your final project is concerned. So in an effort to save time, I've gone and grabbed a clip from a summer video when I did searching, sorting, and Big O in the summertime. So I clipped out a little part of that. I'm going to show you that. Watch it. If I mention summer class or I say we only have 11 classes or weeks, don't worry about it. It's because it was in the summertime. We have 15 weeks. You don't have to worry about me talking about all that stuff. But most of it is content. So when you get the content, you're going to get the same thing that I would have done if I shot the whole video tonight. Then at the end, like now, I'll be live and in person, and we'll do some announcements. Basically, just deadlines, when I'm going to get you stuff, that everything that we're okay, boom, boom, boom. Tell you when me and Hans are going to do the Unit 3 grades. I'm going to tell you when we're going to do the midterm grade, blah, blah, blah. That stuff, all right? So without further ado, watch this, because this is from the summertime, but this is going to go over the first half of your Unit 4 slides. Enjoy. Hey everybody, Lars here. We are going to do the first review video for Unit 4. And as I usually tell the story, when I teach Python, it's a little bit different than when you get an Introduction to Computer Science course when you first go to university. If you first go to university like Rutgers or anything else to become a computer science student, you will take a class called Introduction to Computer Science. Not Intro to Programming and not Programming, but Intro to Computer Science. And what we do is 2 different things. One is we get you started and begin teaching you the first language we're going to use. Here at Rutgers, we use Java. When I was a kid a long time ago and I did my degree, it was Pascal. Now at a lot of top universities, people are starting to use Python. But what happens is as you go through the course, you don't just go through what we're going through, looking at data and the representation of data, then looking at sequences and how to organize our data, then looking at iteration and how to navigate our data. They do that, but they also sprinkle in computer science concepts along the way. And what I do when I teach this course is I think to learn just how to program, sometimes those computer science concepts can get in the way a little bit. So what I do is I extract them, and I go through the process of teaching you how to program, teaching you how to take, logical thoughts and codify them and put them in code and solve problems that way. But I do think those computer science concepts and the different things we do there are important, because at the end of the day, computer science is about seeing how we solve problems with computers, how we solve problems in algorithmic discrete steps where we have a problem state and we start with an initial state and we work step by step to a goal state. So Unit 4 is where you've got the Python under your belt already. Okay, you know the basics of computer programming with Python. Now it's less learning Python and more using Python. So now that you have all of that under your belt, I'm going to reintroduce these computer science topics in this unit. They are simply sorting, searching, what we call Big O, which is really just the examination of the efficiency of your algorithms, and you'll see it's easy and I'm not going to kill you with it. And then we look at recursion. Later, as you'll see, we're also going to look at loading a third-party library and doing some graphs with it, and then at the very end of the unit, I do some exception handling and some things with dictionaries. The exception handling and the dictionary, I'm not going to kill you. You're probably not going to see that on a quiz. But like I always say, I want you to be aware of it. I want you to be exposed to it. Because exception handling, being able to handle when things go wrong while your program is running, is pretty important. And if you program in any professional capacity, you have to do that. It's just the way we create professional code. You have to think of all the things that can go wrong, and you have to handle those situations. And that's all exception handling is. Dictionaries are very important. It's a data structure that is used in Python all of the time, but and I'm going to tell you this story when we start talking about sorting, I've only got 11 weeks to teach you Python. So I've got to make decisions on what we concentrate on, what we do, what we don't do. One of the things I really don't sit on and go over is dictionaries as a data structure. But I want you to see it, so I put it in the slides. Boom, boom, boom. All right. Let's get started. Let's run through what we're going to run through today. The first video, I'm just going to go through basically the first half of the slides. I'm going to go through sorting. We're going to talk about searching, and then we're going to talk about Big O at the end of it, because it kind of tells a linear little story. Let's go. I think I have the slides set up here. If you have a chance, go read about the supercomputer. We're ranked number 2 in the Big Ten as far as our supercomputer is concerned. That is us. Today, the first day of the unit, and this is where I want to be, the sorting hat. The story is this. When you first go to university to become a computer science student, you basically do some of the things you guys have been doing. You learn about the representation of data, integers, floating point, boom, boom, boom. You learn about simple lists. When I was a kid, they were just called arrays. You learn about for loops and iterating and things along those lines. But then, if you take your class in the fall, like I did when I was a kid, around the beginning of October, you are introduced to sorting. And sorting is not necessarily difficult, but there's a whole bunch of different ways to sort data, be it numerical, be it alphanumerical. And for the next couple of weeks, sorts and sorting are the bane of your existence. And because you're young and you don't know what you're doing yet, you wonder, why in God's name am I sitting here bothering with all of these crazy sorts? Bubble sort, quick sort, J sort, merge sort. Why do I care about all of these sorts? When you get older and you get further on in your computer science program, or you turn into an old fuddy-duddy like me and you work at a university, you realize that that is the way that we introduce the efficiency and the examination of algorithms to young students, because the different sorts have different efficiencies. Some are terribly inefficient, like a thing called a bubble sort. You'll see the bubble sort. And some of them are very efficient, like a merge sort and things along those lines. That is what early computer science educators in the 80s were trying to get across to us. They were trying to show us, look, this is the way we solve problems. Some of them are efficient. Some of them aren't efficient. You need to have your eyes on that stuff. So we'll talk about that. Like I said before, I'm teaching Python, and I got to do it, especially in this summer session, in only 11 weeks, so I got to make decisions. And one of those decisions I make early on is I'm not going to have you code up a sort. Usually we would go over the chapter, and I think they do a merge sort in Zell. They may even do a bubble sort, although we rarely do bubble sorts anymore. They really are terribly inefficient. But they're easy to code up, so we want people to code them up and use them and sort their own data along those lines. Basically, sorting is just putting things in order, alphanumeric order, numeric order, from high to low, from low to high. Basically, what every sort does is compares numbers, and if they need to be in a different order, switches them. And some sorts will break things down into different groups and sort the groups and then put all the groups together. Some things will grab an item and compare it to everything in the list up and down the line. There's a whole bunch of different ways to do sorts. And what I do is I give you the web the URL to sortingalgorithms.com, where you can go and watch these sorts run and see all the different kinds of sorts: insertion sort, bubble sort, merge sort, quick sort. They are all there, and they'll even show you them in pseudocode so you can see how they work and what they're doing. All right. You don't have to code up any of the sorts. If you want to, that's fine. There's a couple of ways to do it in Zell in the chapters I give you, but I'm not expecting you to code up a sort and know the algorithm for these different sorts right off the top of your head. As you can see, Python has a built-in method on lists so that you can sort your list anytime you want. And Python uses a thing called the TIM sort. Now, a lot of these sorts have been around since the 50s or 60s. It's funny, the TIM sort has only been around since the early 2000s. So if you want to, go to Wikipedia and read about that. I've always found that very interesting. But as you can see, it's almost like in your statistics class. The first time you see hypothesis testing, or the first time you see confidence intervals, or the first time you see linear regression, you do it by hand. And you're like, oh, this is crazy, this is nuts. But after you do it by hand once and you understand it, then the professor will say, okay, from now on, let the computer do it. Let SPSS do it. Let R do it. It's kind of that way with sorting, too. In computer science, we make students code up a couple of different sorts so they understand the inner workings. And then when they're done, we say, all right, you'll never have to do that again. We're skipping that part. I'm not going to make you code them up. We're going to jump right to the answer, which is, ta-da, using a sort method. So as you can see, I have a list, and I print it, and it's all out of order, and then I just run the sort method on it down here, and I reprint it, and boom, from -2 all the way up to 99, it is sorted. Okay? We can also do it with alphanumerics, with strings. So if you give it a mixed up list and then you tell it to sort, it will sort in alphabetical order if it sees things like that. Okay? One last thing we're going to talk about with sorts is, our magic about lists is that we can have mixed data types in there. I can have strings with integers, with floats, with a whole bunch of different things. But what happens when I try to sort that list and I mix up integers with strings and a whole bunch of other things? And what happens is, you get an error. Because, they always say you can't compare apples and oranges. It's true. You can't compare apples and oranges. So, TIM sort, when it gets Lars in 33 and Johannes in 52, and you can see the Mets are in there, it doesn't know what to do with it. Now, later in your computer travels, you might learn Java, and you might learn about something called sortable, and you might learn about something called comparable, and you might learn that you can teach these programming languages how to sort different things like that. But out of the box, Python's like, I don't know what to do with this. I can't do it. And as you can see, if you read that error on the bottom, it says unorderable types, because it doesn't have the first clue how to compare an integer and a string, because we didn't tell it how. Okay, so be wary of that when you want to sort things with built-in sort functions. Usually they have to be of the same type, so that it's very simple to know what's greater than something else and what's less than something else, and so far along those lines. Okay, now we start out with sorting when we go into computer science, because sorting is very important. We care about sorting, and the reason, and this is good because it gets into some data science-y stuff, we care about sorting because when we first start examining data and getting ready to solve a problem, we want to know as much about our data as possible. Okay? Because if we know certain things about our data, then we can choose certain time-tested algorithms that can find answers for us. If I know my data is sorted, it gives me an incredible advantage when it comes to searching through that data for a particular item. So sorting becomes important, and you're going to discover how important in a second, because we are going to look now at searching. Let's say you have a list of 1 million numbers, and they're not sorted. They're all jumbled together. And I come up to you and I say, hey, can you please write me a computer program that determines whether the number 7 is in that list of numbers you have. So, how are you going to solve that problem? You've got an unsorted list. You don't know anything about your data. All you know is that you've got a list with 1 million numbers in it. Frankly, you have no choice except to what we call go to war on it, or basically look at every single number in that list to see if there's a 7. So you'll start at 0, not a 7, okay, go to the next one. Not a 7, go to the next one. And so on and so on and so on. And if that 7 resides in the last spot on the list, that's the worst case scenario. You will have had to have looked at every item in that list. So, in stats and computer science, we use the letter N to denote population or the size of a list or something like that. Whatever N is, whatever the size of your list is, in this case, 1,000,000, that is how many potential lookups. Whenever you look to see if a number is a certain thing, we call it a lookup. That's how many lookups you would have in a worst case scenario in what we call a linear search. If I've got unsorted data, I have no choice but to do a linear search. I got to look at everything because I don't know. It could be here. It could be. I have no idea. I have no idea what's going on. So if I've got 500 things, worst case scenario, linear search is N500. I have to look 500 times. If I've got 1,000,000, I've got to look 1,000,000 times. Think about big data. Think about some of the data sets Google has, or some of the data sets that they're keeping on customer data in Amazon, stuff like that. A linear search just isn't going to cut the mustard. That's too much data to go through, okay? So, is there a way I can search through data more efficiently and not have to look at every single item to figure things out? It turns out there is, but there's a trick. You need your data to be sorted. And if your data is sorted and you know that it's sorted, then you can do what we call a binary search. Now, a binary search is interesting and fun. Take my same list of 1,000,000 numbers, and this time I'm going to tell you the list is sorted. And I'm going to tell you, does 7 appear? I'll stick with the same number, though it's going to be easy. Does 7 appear in this list? Well, what can I do if my number is sorted? My data is sorted. I can play high-low. I go to the middle of the list. If I have a list of 1,000,000 items, I know the middle is 500,000. I go to the 500,000th item and I look at it and I say, is this equal to 7? And the algorithm says no. So then I ask a second question. I go, okay, is this number higher or lower than 7? And then the algorithm comes back to me and says, this number is higher than 7. What does that tell me? If the middle number of this sorted list is higher than 7, what do I then know? Instantly, I know that my number will not appear in the upper half of that list. So I throw it away. I don't need it. I know my number's not in there. Okay? Instantly, I've gone from 1,000,000 to 500,000. I've cut it in half. So now what do? I repeat the process. I now go to the 250th item and I say, hey, are you 7? And the algorithm says no. So then I say, okay, are you higher or are you lower than 7? And the algorithm comes back to me and says, you know what? I'm higher than 7. I can do it again. I can then get rid of the top half of my list. So now in just 2 lookups, just 2, I've taken 750,000 items out. And I don't have to look at them and I don't have to bother with them. And I can keep going in this fashion until I either find the 7 or I realize there's no 7 in the list. Okay? If this were a linear search, I would have to do 1,000,000 lookups to determine that the number 7 does not appear in my list. But in a binary search scenario, where every time I do a lookup, I can cut my list in half, I only need 20 lookups. Think about that. If I know my data is sorted, I can do a binary search. And if I can do a binary search, instead of 1,000,000 lookups, I'm down to 20. That's incredibly efficient. And then when we're done talking about searching, we're going to talk about big O analysis. And we're going to see binary search is incredibly efficient. So if I have sorted data, I can now start doing sort things to show you. Here I just do it with 16 items and I show you big list, cut it in half, cut it in half, cut it in half. only 5 lookups I can find something in 16. Okay? It's instead of having to look at 16, I only have to look at 5. That doesn't sound so fantastic, but if you take the example of a million and compare it to 20, that's huge. You're going to see it's log n. It's the opposite of exponentiation. We'll get into that when we talk about big O. Right now, I want to show you the code. And I'm going to show you, actually, I have 1,000. I have a million down there. I create a list of a million numbers. And then I search for the worst case scenario, 999,999. And then we'll take a look at how it goes, because if I'm not mistaken, I have coded it up for us. I call this blsearch.py. B for binary, L for linear, because I am a good egg, and I also coded up a linear search down there. We are going to compare the two. But this is the code right here for a binary search, okay? I get it. It looks complicated at first glance. Trust me, it's not. Please, trace through it. Look at what it's doing and how it's doing it. You will find that when you look at this, all it is doing is taking a list, going to the middle of the list, seeing if a number is what I'm looking for. If it is not, then I cut the list in half. Okay? That's all I'm doing. And I do it with indexes. I have a number called mid, and mid is set here. It's low plus high divided by 2 with integer division, because I'm doing an index. I don't want any floating points. And middle is always the middle of my list. So if it's a million long, middle is going to be 500,000. If it's 500,000 long, middle is going to be 250,000. And I keep looking at the middle for the item, and then I ask, is it higher or is it lower? See? Well, I ask lower here, and then I use an else, because if it's not equal to and it's not, lower, then it has to be higher. So read this code, go through this code. For now, I'm going to show you that I have 2 functions here. One is called bsearch. It takes what I'm looking for and a list. And I also have lsearch, which is a linear search, which takes the number I'm looking for and a list. And linear search is just, it goes through a loop and looks for it, blah, 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 blah. So what I do here is I create a list. I use range to create a list from 1 to a million. And I put it in a list called mynums. Then I give the binary search the worst case scenario for a list of a million numbers. Okay, and then I print it. Then down here for linear search, I just give it a random number. It's pretty big though, because we're gonna look at it real quick, and then we're gonna compare it to binary. Let's run this bad boy and see what we get. All right, I set up my binary search so that it prints out a lot of data as it runs, so that you can see it running. So you can see here I have a step counter. I tell you what the mid is. A step counter. I tell you what the mid is. So you're going to be able to see the binary search work. And the step counter is 1, 2, 3. That's how many lookups I'm doing. Every time I do a lookup, I print out what I'm looking for, and then I print out what the mid is, what I'm looking for, all the way up to 19. Okay? And when I get to 19 and the mid is 999999, I got it. I say the number is found. Boom. Okay? So that 19 is how many lookups I needed. Okay? Now, if it wasn't in the list, then I would look up one more time and I'd get 20. So that's the max on a list of 1 million numbers. That's incredible, to be able to search a million numbers with only 20 lookups. But that's what binary search gives you. That's what sorted data gives you. Now, my linear search, I looked and, hey, I found the number. Of course I found the number. It's an ordered list from 0 all the way up to 9999. But look how many times I had to look. Okay, because we start with 0, it's 1 more than the actual item I was looking for. Now, if I do this, and I change this to look for 99999, in the linear search, I'm going to look for the same thing I did in the binary search. And even though it ran pretty quick, it's because it's a computer. If we did this with billions, you would definitely see the difference in efficiency. In only 19 lookups, I found my number. The linear search said, oh, it said number not found. Why did it say number not found? Interesting. Did I do something wrong? What if I gave it a name? Yes, okay. my linear search somehow jumps out before it gets to the very end. Because now in that many passes, I found my number. Okay, I'll have to look at that. Don't you love it when things explode in the middle of videos? So in 19 lookups in a binary search, I find my number. Here, I have to look 999,998 times. Okay? Think about the efficiency. Think about the savings there. I mean, it's incredible. Okay? And it's because we have sorted data. And it's because we know with a binary search we can play high-low and literally throw out half of the list every time we do a lookup because we know our number's not going to be up there. Okay? This code right here, blsearch.py, I'm going to put up in Sakai. And you're going to see with your second homework assignment, I want you to have a binary search and a linear search in a library that you use. You're going to read some random numbers, clean them up, and then you're going to, use different searches on them. Use this code. I have no problem with it. I want you to read it. I want you to understand it. But at the end of the day, if you use this code when you create your library with your binary search and your linear search, I got no problems with it. Check out my linear search though, because apparently something was going wrong with it. I return. Well, I know why I return. I return a -1 if I don't find a number. But why I wasn't finding 99999, I don't know. So I'm going to have to look at that algorithm. But I'm going to give you this code. Okay, so you don't have to code up all that craziness. You have it. But I want you to read through it, and I want you to understand it. Because you'll see when I ask you the question and I give you the homework assignment, you're going to see, how things work, and you're going to want to know the inner workings. And you'll see it's not hard. You'll have this code when you get that. Okay? So that is binary search, and as you can tell, that's what sorting gets you. As you can see here, I used that code when I created these slides. And here I talk about coding up the linear search so you can compare the two. We did that. This is the YouTube video where I'm talking about there, so you're getting all that done. Binary versus linear, the efficiency is insane, and we're about to look at that now. Here I think I do another example and another example. But here is where we start talking about the third topic we're going to discuss in this video, and that is what's called Big O. Now, first time I heard Big O, I thought about this guy because I was a basketball player when I was a kid, and Big O is the nickname of Oscar Robertson, who played basketball for Cincinnati and was a big basketball star in the 60s. There's also Big O, the character in anime. So when people hear Big O, they probably don't think about what we're going to talk about. Big O is notation used by computer programmers when we examine the efficiency of algorithms. The O basically stands for order of magnitude. So it's like order. And we call it Big O because when we do order of magnitude, we care about big things. We don't care about little things. So if the efficiency is expressed like in a polynomial, we only care about the biggest exponent. If it's x to the fourth plus blah, 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 all we care about is x to the fourth. Okay, we care about big things. And there are common efficiencies for different kinds of algorithms in computer science. And what we do is we examine how efficient our algorithms are by thinking of the Big O number. Now, this probably sounds confusing and kooky, but basically the simple ones that you have to think about are Big O of 1 is constant. So if I print my name, Lars, and no matter what the algorithm sees or no matter what it does, I'm just going to print Lars, well, it's the same result every single time. So it's constant. It's Big O of 1. When I have a task that maps to the size of my data, like we did with a linear search, then Big O is N. So if my list is 1,000,000, then N is 1,000,000, then that's what the Big O is. It's N. It's whatever my data size is. Because in an unsorted list, I've got to look, I potentially, worst case scenario, have to look at all of the data. We always look at the worst case scenario because we don't want to get bit in the rear end when we do efficiencies. Some people will say, well, can't you just, do the average, do the. No, you can't, because the minute you start planning on the average won't happen. Murphy's Law exists, believe me, and it is Very strong when it comes to computer science. So we always, when we look at efficiencies and algorithms, look at worst case scenarios. Okay. So a big O for a linear search is whatever the size of the data is, or n. The binary search is different here. I believe I went to Wikipedia and stole a graph to show you some big O complexity numbers. A binary search has big O of log n. And if you remember your math classes when you were in school, I don't know when you get logs. Do they even do logs anymore? Logarithms are basically the inverse of exponentiation. So where exponentiation gets big, and you can actually see some on that graph, log is the other direction. It gets small. You can see here it's red. It's right here very close to the actual number itself. You can see O of n, which is a linear search, maps 1 to 1. These dimensions are weird, but you see that's 100, that's 100, boom, right there. So if it were 70, it would be 70, 50 would be 50. O of log n is super efficient, so it's super low. So if you had 100 elements to search through, it's incredibly small, the number of lookups that you would need. Because think about it, for 100, you'd go 50, 25, 13 down the line. It would be like 5 or 6. Okay, so that's how efficient the binary search is. The big O for a binary search is log n. Now then we can get some bigger ones. We can get like n log n, which is like, I don't know, merge sort. That's for a lot of things that get divided up and then put back together. Then we start getting into the big boys. Then you get n to the second. Then you get 2 to the n. And finally, every computer programmer's nightmare is n factorial. Okay, look at that. You can see how these efficiencies rocket off the screen. Those are problems which are what we call intractable, where if we had all the time in the universe and all the space in the universe, we still wouldn't be able to attack these problems because they get huge fast. There's a very famous problem called the traveling salesman problem. If you look it up, it's traveling salesman problem, or TSP. And you can see basically all it is I'm a traveling salesman. I've got to go to 5 different cities, find me the shortest route. That's it. That's the problem, basically, simply put. Problem is, once you get greater than 12, 13 cities, you're running into problems because you literally have to look at every single route, and it's 13, 14 factorial. It's 13 times 12 times 11 times 10 times 9. That's how many routes there are. And pretty soon that number gets monstrous. I mean monstrous. I mean so big you can't. I mean, I think if you go factorial 22, 23, I forget what the number is, you all of a sudden are more items than there are stars in the universe. It gets insane. It gets crazy fast, real fast. Some of those problems are interesting, and the way we tackle them is not with algorithms, because algorithms can always find you the solution. We deal with heuristics. We deal with things that'll get us close, that'll approximate what we think. And there are some decent heuristics and approximations for the traveling salesman problem, but still, it's pretty huge. If you want $1 million, go to the Clay Mathematical Institute and study up the P versus NP problem. That's pretty much what you're dealing with when you're dealing with big O of n, factorial. Those are the kind of problems, and I'm not going to get into polynomial versus non-deterministic polynomial, but those are the kind of computer. That's like the biggest problem in computer science. But I digress once again. I don't want you to think, oh my God, I haven't done logarithms in a while. Oh my God, I don't want to deal with factorial 22, factorial blah, 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 blah. You won't have to. Again, I want you exposed to this. I want you to see it. I want you to understand that your linear search is O of n. So it goes up as the number of data items goes up. I want you to understand that a binary search is O of log n. So it's very efficient, very, very small, even for big, big numbers. I mean, it's only 20 lookups for a data set of 1 million items. Okay? So I don't want you to worry about big O. I want you to see it. I want you to feel it. I want you to understand that when we have algorithms, we do examine them to see how efficient they are, and we have ways of, saying, oh, this one has big N of N log N, so we can understand the efficiency is going to be this. It should take this long to run on this much data, blah, blah, blah. We want to be able to do that, and this is how we do it with big O complexity. Okay? All right. Then that, if I'm not mistaken, and I have some other rather technical looking things here. Oh, okay, and I talk about P versus MP in the slides. And then we get to the break. Okay? I'm saving recursion for the next time we meet. The next time we meet on YouTube. Hey, everybody. Back to 2017. Back from the summer of 2016 to 2017. Just to drop you a note, even these announcements, they're going to be quick. Basically, I'm going to let you know that today is Monday. I'm going to produce this video and hopefully get it up before the end of the night. Then tomorrow, it's going to be a big day. I'm going to get you the recursion video. I haven't decided whether I'm going to try to recycle one like I did tonight or whether I'm going to just shoot it live because it's kind of quick. But it's good. It'll show you recursion. It'll show you an example of recursion and the way I think about it, and I think you'll get a kick out of it. Then tomorrow night, I'm going to get you the assignments. When you see the assignments, you're going to realize why I didn't give them to you tonight. Because assignment 1 deals with recursion, and you haven't gotten that video yet. And assignment 2 deals with linear search and binary search, and that's what you got in the video that we shot tonight, okay? I am aware that I need to finalize groups. We have 15 people. I have 2 groups already, so I'm in pretty good shape. We have 16 people. So there's 2 more groups to go. I'm going to create them, and then I'm going to list them, and you're going to know what your groups are, and then I'm going to release the information sheet on the final project, probably Wednesday. Remember, I build spring break in, so I figured we weren't going to do anything. Forget about you. I didn't do anything, so I enjoyed my spring break as well. But now it's time to get up and get going again. It's the 20th. We've got 10 days, so we're in pretty good shape. I want to get you all your resources by tomorrow or the next day so that you're ready to rock and roll. But this unit isn't exactly great shakes. I almost consider it a rest between Unit 3, which is a big boy, and Unit 5, which is a big boy. But we have time. You can use the time to get organized and start thinking about things for your final project, frankly, during this time. Okay? So I'm going to get you the second video, hopefully tomorrow, which will be Tuesday night. And then I'm going to get you your assignments at the same time. And then Wednesday, Thursday, I'm going to dribble out the information on the final project, your groups, what the final project entails. There's 3 different sections of the final project. You're going to do a proposal, then I'm going to approve it, and that's going to be the first 10, 12, 14 days. Then you're going to do a design document, then you're going to do the final program, the code, and a small demonstration. We're not demonstrating in class. It's going to be like a Prezi or a PowerPoint or something along those lines, okay? But just dropping you a note to let you know I'm back on the job, and we're going to get things going as far as Python is concerned. Hans and I are already looking at Unit 3 stuff for grades. This coming weekend will be the first weekend I'm not in Seattle or I'm not running a basketball party this month. So I'm going to settle down and make a pot of coffee and start looking at your midterms and getting that squared away for you. So we're going to get some progress made this week. The unit, again, doesn't close until March 30th. So you're in good shape. You got no worries, all right? Then I'm going to get out of here. You be good, and I should be back in the next day or so with your recursion video and your assignments, all right? Good. Then I'll talk to you soon. Bye.